what are empty sets, finite sets, and infinite sets. So basically these are three types of sets which we need to know, okay, because there is a lot of use of the empty sets at many places, and we also need to understand what are finite sets and infinite sets. Okay, so first of all, let's try to understand what are empty sets. Generally empty sets are also called null sets or void sets. Okay, so let me just write it. Null. Okay, so this is empty set. This is the general other terms which are used in many books and by other teachers as well to represent empty sets. So what is empty sets? Empty sets, as the name says, that a set which does not contain any element. Like if it does not have any element, then we can say that it is an empty set. For example, we have a set which is represented by A and it does not have any element. I'm representing it in the roster form. It does not have any element. Okay, so we will call it as empty set. And there is one more representation of empty set which is generally by the letter phi. So whenever we write phi, we don't need to represent it in braces or curly brackets. So a, if it is an a is an empty set, we can represent it as phi also. So let me give you one other example. Suppose there is another set and it is defined by x. Now I am writing it in set builder form. Okay, x and the condition is x belongs to whole number. Now see here, there is a set which contains the element x, and x should be between 0 to 1, but x is also a whole number. So the question is saying that we have to represent all the elements, all the numbers which are present between 0 to 1, and the number should be the whole number. So remember, what are the whole numbers which we have? The series of whole numbers starts from 0, 1, 2, 3, 4, 5. Okay, so we don't have whole numbers as in points, right? So as we can see that there are not any possibility of writing whole numbers between 0 and 1. So this will be represented by empty set or phi. Now let's see another example. Now I write a set B and I will represent it as x square equals to 4, and the condition I am giving is x is odd. Okay, so first of all, in this case we will have to write the elements x of this set. How can we write the elements of this set? That means the solution of this particular equation, x square minus 4 or x square equals to 4, right? This is the equation. We will have to find the solution. X square minus 4 equals to 0. So the solutions will be x equals to plus 2 and minus 2. So now the other condition which is written here is x should be odd, but here in this case the x is not odd, right? So is there any possibility of writing the set B? I don't think so. So we will represent set B as a null set because there is not a possibility of writing any element, and we will also represent it by phi. It is not necessary to represent it in both ways. You can write either way, either phi or braces, but generally we represent it as phi because it is a short form. So now let's understand what are finite sets and infinite sets, right? So first of all, let's see finite sets. Suppose I have a set A which contain element 1, 2, 3. Okay, so as we can see here that the number of elements in A are represented by this 3, which is a finite number. So we can say that A is a finite set. That means, as per the name suggests, a set is called a finite set when it has limited number of elements. Take another example, set B. Here I will write X, again I am writing it in set builder form, right? So this is the set which I have written X, and X is a solution of x square minus 4 equals to 0. So as we can see that x square minus 4 equals to 0, which is a quadratic equation, and it has two solutions which are real, which are plus 2 and minus 2 as per the solution. So we have the elements, if we represent it in roster form, then the elements will be plus 2 and minus 2. So here we can see that the number of elements are 2, so it is a finite set. Take another example, set X I'm writing the same example. Sorry. So this is the set which I have written, and now it is the same example which I gave into when I was explaining you the empty sets. So the solution for this is an empty set, right? Because the values, the elements which are coming for this particular equation will be plus 2 and minus 2, but the condition is written that we need x should be odd. So it is a empty set, and it is represented by phi also. So this is also an example of finite set because this the number of elements are 0 and 0 is a countable digit. So we categorize empty set as a finite set. Okay, phi is finite. Let's see another example. X and here x belongs equals to n and n belongs to natural numbers. So this is a set which I have written, and if I will write it into the roster form, then what will come? 1, 2, 3, 4, and then so on. So here in this case, the number of natural numbers are infinite, because infinite means we cannot count. There are not countable digits over here. So such kind of sets are categorized into infinite sets as the name suggests, right? So we can say that it is an infinite set. Infinite set. So now I will give you some examples as well. Okay. So this is a set A. X X is solution of x square plus 2x plus 1. This is the equation. So is it a finite set or an infinite set? Since we all know that the equation x square plus 2x1 plus 1 is a quadratic equation, and it will have only two solutions, either may be real or imaginary, that will we can calculate after finding the solutions. Okay, so the solution will be either rational or irrational, but there will be only two solutions, so there will be two number of elements. We can say that it is a finite set. So let the solutions be a and b. I have not found the solutions, but I'm just writing that there will be only two solutions, so it is categorized into finite set. So let's see the next topic, equality of sets. So now we'll see the equality of sets. That means we'll check whether the sets are equal or not. How we can check when the two or more given sets are equal or not? So let's start with an example. I have a set A represented by 1, 2, 3, and there is another set. Another set B containing elements 2, 3, 1. So if I can see the elements in A and B, the elements in A and B are 1, 2, 3, and again if I rearrange the elements in B are 1, 2, and 3. So the elements are same in both the sets. That's why we can say that set A is equal to set B. However, it does not matter the arrangement of the elements or the order of the elements. See another example. Now let's take another example. X equals to P Q R. So these are the elements of X, and I'm taking another element, another set, I'm sorry. Y as P R S Q. So now we'll compare the elements of X and Y. See, as we can see that the elements of X are P, Q and R. So the sets X and Y has different elements, as we can see here. So the set X has the elements P, Q and R, and the elements of set Y are P, Q, I'm writing it in sequential order, R, and there is an extra element is in this set which is S. So as we can see from here that we can directly conclude from here by observing that the elements of X are not equals to the elements of Y. So we can say that X is not equals to Y. Fine. So now see, there is another example. Suppose there is a set C, and this set contains elements 1, 1, 2, 4, 5, and there is another set D which is represented here in the roster form, and it contains elements 5, 2, 2, 4, 1, 1. Okay, so these are the two different sets, and we have to find whether these sets are equal or not. Okay, so let's first check the elements. So the elements which are present in set C are 1, 2, 4, 5. So these are the 4 different elements present. I am not considering the repetition of the elements. Fine. So now let's see the set D. The elements which are present in the set D are 1, 2, 4, 5. I have written them in the sequential order, as you can check. So again, I have not repeated the elements because it does not matter to me. I just have to check the elements which are present. That's why we generally do not repeat the elements in the sets. So in both these sets we can see the number of elements are different, but the elements are same. So we can conclude that set C is equal to set D. And one more thing, from this example we can conclude that when two sets are equal, then it is not necessary that both the sets should have the same number of elements, right? When any set A is equals to set B, it does not implies that NA equals to NB. Fine. So this is the equality of sets which we can check.